On this week's MetPy Monday, we're going to continue looking at the freezing layer rules of thumb and make some violin plots. Welcome to another MetPy Monday. Hello, I'm John Lehman, a software engineer for Unidata. On this week's MetPy Monday, we're going to continue looking at the freezing level and some rules of thumb around it that we started a couple weeks ago. But this time I'm actually going to be going through a notebook because you'll see there's quite a bit of typing involved, and this is the only way to keep this video relatively short. So first, as always, we're going to do our imports, pandas, numpy, datetime, MetPy's unit support, and the Iowa State Upper Air Simple Web Service from Siphon. Now, in an effort to get a decent sampling of data, but also to not take a long time to run, I'm going to get the 0 and 12Z soundings from each month of the year 2020, and just on the first day of the month. This will let us see if this freezing rule of thumb business has any seasonal variation, maybe. So I've got a variable here for year of 2020, so I could change it easily, creating an empty list of date times to get. And then we're looping over months from 1 to 12. And then in each month, we take 2 times the 0Z and the 12Z sounding. And we append a date time with that year, month, the first of the month, day, and that time to our date times to get list. Then we're going to use the Iowa State request all data to get all data for a specific date time. And then we're going to call date times to get .pop, which will take an item off the list and actually remove it from the list. And that will give us our initial data frame. So now we've got one time for one day. Then we're going to go ahead and run this loop for the rest of the date times to get. So the reason that I did it this way was so we had a data frame that we could later use the concat operator on to concatenate that data frame and what we get back from the request all data for a different date time. So as you can see, we're chugging through the date times here, but I'm on a rather slow internet connection, so it's going to take just a little bit for us to get all of those. At the end of that, we have a concatenated data frame where we have 2 time samples from the first day of the month for each of the 12 months. So we'll let that data go ahead and download and continue. Okay, so now that we've got all of our data downloaded, it's all concatenated into one giant data frame with over 250,000 rows and the normal 10 columns of data. So now I'm going to create 2 functions, one to calculate the freezing level based on the rule, and one to calculate it based on observed. Now these are exactly like what we did last week. So I've just put them in some functions. We're finding using argmax, where the pressure is the maximum or the surface, and that's giving us the surface temperature. And we're getting that value, and then we're saying we're using a lapse rate of 2 degrees per 1,000 feet. That's 2 degrees Celsius per 1,000 feet. And then we're returning now the max of either 0 or the predicted, because I don't want to be able to have a negative freezing level. If the surface temperature is below 0, that's what we would get out of here. Okay, now for the observed. This all works just basically the same way as before, with this little addition of if the surface temperature is below 0, we're just going to return 0 once again. And other than that, we're doing a linear fit. So we go ahead and run these cells to define those 2 functions. And now we've got a big loop. In this loop, we're creating a results data frame that has the columns time, station, rule, and observed. Then we're going to do some loops. For each unique time, we're going to create a data frame that contains just the data from that time. And then for each unique station that we've got, We're going to loop over that, create a data frame that's got just the data from that station in that time. We're going to drop anything that doesn't have both temperature and height, as we require those. And if that leaves us no data, the length is 0, then we're just going to continue. We're going to go back to the top of this loop and go to the next station. Then we calculate the rule, calculate the observed. Here I've made the decision that if my observed freezing level is greater than 0, I'm going to append to my data frame the time, the station, and the results that we just calculated. But if it's 0 or for some reason less, then we're not going to append it. I don't need a rule to tell me what the freezing level is if the freezing level is observed at the surface. So we run over those calculations, and occasionally we get something about polyfit being poorly conditioned because maybe we don't have enough data around, maybe the freezing level is very close to the surface. And we've done our calculations. So now if we look at that results data frame, we've got 2,216 rows for time, station, the calculated rule, and observed value. Remember, these are going to be in feet above ground level. I'm going to calculate an error column, which is just the rule minus observed. And then we're going to make a plot. And this is not necessarily the most efficient way to do this, but what I want to do is say, for all of the stations at 0Z and at 12Z for each month, calculate the error. And then we're going to make a violin plot of that. Well, we've already done the error calculation, but we need to split it up into 0 and 12Z. And this is the quickest way that I could do that. Unfortunately, using the NumPy datetime object as pandas does makes interfacing with normal date times a little funky. So we've had to use datetime, UTC from timestamp. We take our times, turn it to a list, and divide by 1 times 10 to the 9th to get nanoseconds into seconds. And that works. Then we're setting the hour to be 0 and the hour to be 12. We're using violin plot, so we can get an idea of what does the distribution of this data look like. What are the max? What are the min? Is it clustered around one value? Is it skewed somewhere? And we're going to do this plot with tick labels of 1 to 12 for each of the months. And I put a 0 line on here. And what we get, here's our month along the x-axis, the error in feet along the y, and that 0 line being the defining line of, do we care about being above or below 0? Well, do we want to predict a freezing level that's higher or lower? It depends on what the application is. If you're using the application for aviation, you probably want to predict a freezing level lower than it actually is, so nobody accidentally gets into trouble. Maybe in some other applications, you might want to predict it higher than it actually is. And then the different colors would be 0 and 12Z. So there's some relatively interesting things that I can pick out just from looking at this. Some of the times we've got more negative biased air. Others we have more positive biased air. So 0Z, we're more positive biased. 12Z, we're more negative biased. Also, in certain months, we can definitely see a change in the middle of the year. We tend to have more higher positive biases, or higher maximum positive biases. So just by playing with the soundings, playing with the numbers, we were able to make this plot, which uses an astounding amount of data in just less than 100 lines of Python. So it really is incredible, the analysis power that we can harness with Python, MetPy, Siphon, and then some of these wonderful data sets, such as the Iowa State Archive. I hope that you found this useful, and I'll see you on next week's MetPy Monday.